Hello, and thank you. Yeah, so I'm going to present results from the HERA Impact Simulation Group. And as you've just heard, HERA is European's ESA's contribution that is planned to contribute to AIDA. And so there will be more slides, of course, on HERA. And so I won't go into mission details, but so the importance, of course, of HERA is to characterize the binary system, the moon, D must be, and also the Dart crater. And so what we started to organize, and so we have a HERA Impact Simulation Group that is shared by Kai Wünnemann and Martin Jutzi. And we have members from both the planetary science community, astronomy community, so with experience in small bodies and cratering, and also from the hypervelocity impact and engineering community. So we have members from the Fraunhofer Society, and from France we have Simchock and SEA. And so in the working group we have the experience on different numerical approaches, so like ALE codes and also SPH codes to do modeling. And however, we also have experience in experiments, including also two-stage like gas experiments to do cratering. And so on this slide, on the top left, I also show some snapshots from impact experiments that have been conducted at the Ernst Mach Institute in Freiburg in the framework of the Mehmen Research Group. And so yeah, you see the ejector plume for different target materials. And the nice thing, of course, of the experiments is that you can directly observe the ejection processes and measure parameters there. And for modelers, this is very important because this is the ground truth to validate our models. And yeah, on the other hand side, we have the models, and they allow us to do systematic parameter studies, and then also to scale from the laboratory experiments to natural scales. So we combine the advantages of both methods in our group. Okay, so what are the goals of the Impact Simulation Group? Of course, we work complementary also to the Dart benchmark or modeling group, so led by Angela Sticker. And so we also want to derive, of course, the efficiency of the whole impact momentum transfer, so the beta values. And we also want to assess the different range of crater morphologies, what is the depth, what is the diameter, and so on for different target properties. Okay, we started actually to do a benchmarking for the different codes that we have. And so we have two test cases, and this is the first test case that is coming from the Dart benchmark study that has been submitted recently, so Stigl et al. Icarus. And so the scenario is that we have an aluminium sphere impacting with 5 kilometers per second onto an aluminium target that is assumed to be or strengthless or to have a constant strength here. And in this benchmarking, we have 3 codes participating. So there's the ISIL code that already is included in this study. And then we have from SEA the HERA code, and from Simchock the Radios code. And so here are the results for this scenario. On the left side, you see the evolution of the diameter, so the diameter versus time, and on the right side for this experiment is the depth versus time. In blue, you see the HERA results, and in red is ISIL, and for the constant strength case in black, there's Radios. And so the top curve here gives you, of course, the strengthless case, and so the crater is still ongoing to grow in this scenario, in this case, whereas it has ceased growing already in the constant strength case here. And so we analyzed the deviations between the different codes, and so here the deviation is in the order of a few percent, 1 to 2%. When we include a third code here, it's slightly growing to up to 4%. So however, deviation is small, and it is in the range also of, in the range of the results of the Dart benchmark. As next, we also want to compare, of course, what are the effects on beta, what are our results there. And therefore, we have a second case that is more realistic in terms of the real Dart impact. So we have an impactor with 500 kilograms mass impacting with probably an older value. This is 6 kilometers per second. However, this is constrained. That is the input to all the modelers in the group. And yeah, the goal is then to show what are the differences, assuming different target properties. So this is left to the modelers. And of course, we want to see what are the differences for the different codes, but also for different modelers using the same code. Okay, so here we have just a short summary. So we have participation here from ISAIL, from Raducan et al., and also from Luther et al., with rather similar setups, I would say. So there's a projectile with a certain porosity assumed. So here it's spherical, here it's a cylindrical projectile impacting with this 6 kilometers per second onto a target, or it's homogeneous. Here in this case, we have a homogeneous height and also the case of layering. And so we've assessed different properties, different cohesions, of course, different porosities, and different coefficient of frictions. In the case of the layering, the top layer is more porous than the bottom layer. And yeah, okay. We also have results from SPH codes. So these are the groups Meinl and Schäfer and also Jutzi et al. And there we have a cohesion of about 100 kilopascal for this impact. Okay. And so here are the results, first of all, again, for the diameter. We also tested, by the way, in these slides, how do we perform against scaling law results. So in color here, for the diameter against different, so here the coefficient of friction and here the porosity, you see results for different scaling parameters put into the scaling laws from Hausen and Holzappel, and the parameters are from Prieur et al. 2017. And the black results give you results using the ISIL code. And so what you see that, of course, with the increasing strength, so the increasing cohesion, the crater diameter is decreasing, but also with increasing coefficient of friction and increasing porosity. And so in general, those results fit quite well to each other. And so that we, as in the next step, wanted to show, of course, okay, the better values. Okay, don't know if the battery is not working out. Okay. Okay, I think I skipped these slides a bit because it's going too much probably into the details of the method. But I just stressed the points that we use tracers that follow a continuum flow in the grid to analyze the ejector. And I stressed the point that validation, of course, is important, and that is what I show here. So what you see here is for a sand-like target, so properties are 40% porosity and the coefficient of friction is 0.6. You see ejection velocities against the launch positions from the crater center to the rim of the crater. And here you see ejection angles again against the launch position. And here are experimental results from Schindler et al. 1999. And so we have a good agreement here. And that is, of course, the basis to derive then better values based on reliable ejection data. Yeah. Okay, and here we have results for beta. So beta versus the coefficient of friction here. So this is user 1 using ISAIL. And the different colors show an increase of the coefficient of the cohesion. And these are results of 20% porosity. And what you see is that, first of all, with increasing the cohesion, so downwards here, you have a decrease of beta, but also with an increase of the coefficient of friction, the beta values decrease. Here are results from the second user having a slightly larger porosity, but yeah, the general trend for similar cohesions is the same, that the beta values decrease with the increasing coefficient of friction. And I mentioned also the layered case that plots down here with the top layer of 50%, but a very small cohesion, and that fits, showing the same trend again, but fits similar to the 20% porosity case with the high cohesion. Okay, and here are results of the beta value against the porosity. Again, from user 1 using ISAIL. So again, the increase of the cohesion leads to a decrease of beta, and an increase of porosity also leads to a decrease of those beta values. So this is really important. Yeah. And here it's getting more interesting. Here we have I would say, equal target properties from user 2, yeah? Those crosses here. And there's a slight deviation, and this deviation is about in the order of 2% to 4%, based probably on the projectile setup, equations of state use, but also modeling parameters, further parameters in the parameterization of the compaction models. Then, there's also the case with 50% porosity from the layered scenario, and that is also plotting slightly off by 5%, but I would say in general that's still a good agreement. Then we have here results for the SPH codes using the high cohesion here of 100 kilopascal, showing again the same tendency. So user 3 and user 4 with an increase of the porosity, you have a decrease in beta values. And we also analyzed the deviation between those two users using SPH, and the deviation is in the order of 4 to 5%, similar to the deviation between the two ISO users. And when you take into account the different codes used here, the different numerical approaches, this deviation can grow up to 11% in this case. So it's slightly larger, but is still in agreement also to the deviations that have been shown in the DART benchmark study. Okay, I try to come to the conclusions. Yeah, okay. Of course, what you also see is, and this must be stressed again, yeah, that the largest deviation, yeah, between for beta is, of course, depending on the target properties. So there you have a deviation of 45% here. And so the target properties are really the key here and are crucial. And what Sabina also mentioned and stressed is in the talk before, this is important that for similar beta values, of course, you might end up with different target properties that fit to this beta value. So we have to assess also crater morphology and crater size. No, it's going too quick. Okay, the conclusions. So, of course, we want to give reliable predictions with our modelings, and we aim also at validating our models. So what we find for our preliminary results here is a good agreement in order of few % deviations between different users using the same code, but also different codes perform very well in the order of 10% deviation only. And so the results depend on, of course, the target properties. And so the cohesion is really an important factor here, but also the porosity and the coefficient of friction must be analyzed. And the layering plays a role. And as we've seen before in other talks, also the projectile setup and geometry might have influences on the results. And so that is what we want to analyze also in the next step. We want to go more into detailed comparisons for the different crater morphologies and betas depending on the target properties. We want to include studies on the local topography or shapes. And we want to do further comparison also to experiments, like, as I said, for validating also the models. And then finally, we want, of course, to compare the DART crater with target properties and our input from the model. Okay, thank you.
Thank you, Robert. You have time for a couple of questions.
Pete Schultz from Brown. I noticed in your ejecta velocity distribution, you matched it very well with Centella's data. There's another couple other data sets, both from Hausen as well as from work I did with Brendan. It's about a factor of 2 higher than what you saw here. Have you looked at those data to see how they compare and why they're off?
The ejector velocity. On the,
yeah, ejector velocity.
Okay. Yeah. So we had a look also on different experimental results. Yeah, but so in Hausen and Holzapfel 2011, there were more results, I think. And they had different target properties also, and we did modeling for this. And this seemed to compare well as well, yeah. So, so there's a deviation in the target properties, and we can reproduce the experimental results also by modeling. But
I was just curious that we were a factor of 2 higher than what Centella showed, and you matched very well with Centella. So that's why I was confused. It was a paper published back in 2010, 2011. Anyway, suggest we can talk later.
Yeah, okay.